Well, hi everyone, and welcome to the August installment of the SLCan webinar series. Today we're very pleased to have with us Shane Love, who's going to be presenting on planning for pedestrian-induced vibrations in a laboratory. Shane brings his expertise in structural dynamics to RWDI's damping systems team and their acoustics, noise, and vibration group. Their clients benefit in particular from Shane's ability to maximize the efficiency of supplementary damping systems by applying his nuanced understanding of sloshing dynamics and non-linear dynamic systems. Whether he's devising structural mitigation strategies to limit footfall vibrations in a busy hospital or solving structural control challenges in an ambitious skyscraper, Shane's research background and international project experience combine to deliver successful outcomes for building projects. I'll turn it over to Shane here in a minute. I just would remind everyone, if anyone has any questions throughout the presentation, to please key them in the questions box on the dialog box of the webinar, and we'll review them all after Shane has done his presentation. So without further ado, Shane, I'll turn it over to you, and thanks again.
Okay, thank you very much for that kind introduction. So we'll just jump right into it. We're going to talk today about planning for pedestrian-induced vibrations in a laboratory. So first, we'll give an overview of the presentation. We'll talk about how vibration problems arise. So with any sort of vibration problem, we always have a source. That's the thing that's creating the vibration. And then there's a transmission path, and that's the medium by which vibration moves from the source to the receptor. And the receptor is the thing that is being affected by the vibration. So in most cases, it's either a person, they're objecting to the motion of the floor that's interrupting their work or their life, or it's equipment. And we're mostly going to be talking today about sensitive equipment. So we're concerned about the vibration getting through and shaking that microscope or shaking that MRI or whatever the piece of equipment is and causing it to have performance issues. And once we know what the vibration is that the equipment is experiencing, then we need to compare it against some sort of criteria to evaluate whether or not the equipment will perform as anticipated. So that's the general kind of linear flow of vibration from source through to receptor. But I'm going to begin with the end in mind today. So the first thing I'm actually going to talk about is kind of the last stage, where we're going to talk about the receptor and the vibration criteria. And the reason for this is I want us to know the importance of vibration and just understand what sorts of things we ought to be looking at. So we'll begin with the end in mind. And then we'll move on, we'll talk about the source. We're focusing specifically on footfall vibration for this presentation. And then we'll move on and talk about the transmission path. And more specifically, we'll talk about some of the modeling and measurement techniques that are typically used to evaluate pedestrian-induced vibration in buildings. And then at the end, we'll talk about some design and mitigation. So just some of the kind of experience, the rules of thumb that we tend to use when we're evaluating a project for footfall-induced vibration. So let's start by talking about the receptor and the criteria. And the image I like to start with when we're doing these sorts of presentations is a colored scanning electron microscope image. And I have a couple of images that I'm going to show here. The first is shown here on the left, and it's a picture of an image of an E. coli bacterium taken under what I'm going to call ideal conditions, so very, very low levels of vibration. And you should see that this is a fairly clear image. There's a lot of detail that we can make out of it. We can see all sorts of different colors and different, I guess, densities of colors in here. I'm not an expert on E. coli, but a researcher can look at this, and this is a sharp and a very crisp image. Now let's contrast that against the same E. coli bacterium being scanned, but now it's under a much more higher vibration environment. And if we look at this image, yeah, you can see it's kind of got the same sort of outline, but it's much more blurry. So these vibrations are roughly 10 times higher. And just by doing that, we can see we don't have the clear contrast in all the different parts of the cell, but we're looking at a lot more blurry of an image that could affect the image quality, the performance of the equipment, and that might be detrimental to the researcher's study. So when we talk about vibration, we want to talk about criteria, right? And what I'm showing here is the vibration criteria, or generic VC curves. And this is just well, it's a legend that we're going to see throughout the presentation, but it's got the various classifications of vibration. And I'll come to this a little bit on the next slide, but we start with very large vibrations at the top, and then as we move down, we get to very, very small vibrations. And what do each of these different classifications mean? Well, I've outlined a little bit here. We start with workshop, which is kind of the highest level. Above just means it's higher than even workshop. And workshop would be acceptable, say, in a factory type setting where there's distinctly perceptible vibrations, but people aren't necessarily doing, sort of activities where that's a problem. And so they're very perceptible. Below that, we have the ISO office criterion. Right, and that's applicable to, say, an office environment, surprise, surprise. And I'll state that when you move from workshop to office, you're reducing the vibrations by a factor of 2. So office has half the vibrations as a workshop, and residential day is half again. Basically, every single time you move from one class to another, you're basically cutting the vibration in half. So underneath office, we have residential day and residential night, and residential day is maybe acceptable for a home. Residential night is a little bit more stringent, and it might be acceptable in a sleeping area. And we come across this most often in like hospital recovery rooms or patient rooms, where you can still just perceive the vibrations at this level, but it's not necessarily going to affect your sleep or your recovery in any way, so that's sufficient. Now, operating theater, the one in the middle there, is very important because it's kind of the baseline against which many of the other criteria, or other classes rather, are evaluated, and it's the threshold of whole body human perception of vibration. So at the ISO operating theater criterion, that's where the average person can just begin to perceive vibration. So at levels higher than that, people can probably feel it. At levels lower than that, people probably cannot feel the vibration. And once we go less than the ISO threshold of human perception, we're moving out of kind of the comfort realm, right? We're not talking about human comfort anymore. Instead, we're talking about very sensitive equipment, because no one can feel these vibrations, but the equipment might feel the vibrations and it might respond negatively. So VCA would be acceptable in kind of a general lab environment. VCB would be a little bit better, and it's for, say, a CT scanner in hospitals or medical facilities. VCC, MRIs, and NMRs, nuclear magnetic resonators, so more sensitive. And then VCD becomes very sensitive, where we're talking about transmission electron microscopes. Scanning electron microscopes often fall in the VCD range, and we're looking at here 30,000 times magnification, so quite a lot of magnification. Now there's VCE and NIST-A shown for extremely sensitive equipment. There's VCE, there's VCF, there's actually VCG as well. And these are extremely low levels of vibration, where even kind of just a slab on grade location might struggle to hit these. These are extremely challenging to meet. If you see VCG in a project, you can expect that you're going to need to do some very severe mitigation to ensure that that vibration criteria is met, even if that is located in the basement of a building. So this is what the vibration criteria actually look like. So I just had the various classes listed on the previous slide. On this one, we're actually looking about how we evaluate if we know we're achieving VCC or VCA or whatnot. What we have here is a plot, and I've highlighted in red the ISO operating theater condition. So that's the threshold of human perception. And then equipment criteria is below that, comfort criteria is above that. And when we look along the horizontal axis, I've got frequencies in 1/3 octave band frequencies, and along the vertical axis, it's RMS velocity expressed in micrometers per second. So I'm not going to dwell too much on this slide, but I just want to give an indication of what this is trying to convey. And you may have heard the term octave before. Octaves, comes across in music or in acoustics, right? And an octave is kind of it's a measure of the pitch. It's the frequency of the vibration. We can think of a high pitch or a low pitch. That's a high frequency or a low frequency when it comes to acoustics. And same with vibration, because any signal is made up of a bunch of frequencies that are kind of interacting together. And what we're doing when we're comparing against a plot like this is we take our measured signal that's going to have a bunch of frequencies in it, and then we're breaking it down and looking at the various frequency content that's in each, I guess, bin of the signal. So it's just a signal processing technique, and we plot it against this curve. We have a few examples later in the presentation, and then we'll just see how we fare. If all the curves fall beneath, or if our measured curve falls beneath the VCC, we know you've achieved VCC. If a part of it goes above VCC, then we know we're a class higher. So I'm not going to dwell on that, but it is just a signal processing technique. We take a signal, we process it a bit, and then we compare it against these criteria. Now, that's generic criteria that I've been talking about. There's also equipment-specific criteria, and that's the preferred approach, right? Because the manufacturer would know best how much vibration their microscope or their MRI or whatever the case may be, how much vibration that equipment can tolerate. And so they ought to be able to produce a plot similar to this. This is just one example, of course, that's showing the amount of vibration that it can tolerate. In this case, it's versus various frequency. So this plot here is similar to one before. It's just a different curve, and it's expressed actually in a different way. If we actually read the text that's with this manufacturer's specification, it's asking for the Fourier transformation. That's a different method of processing the signal, but it's still breaking it down, and we're looking at different frequency content here. And so we see in this plot along the horizontal axis, it's frequency, and then a measure of acceleration, or the amplitude of the vibration, is along the vertical axis. So again, we're just taking a signal, we're comparing it against a curve and making sure that everything's going to be okay. So this is the equipment-specific criteria, and it's ideally what you want to use in a lab environment. You'd want to know what equipment you're using, get the vibration criteria provided by the manufacturer, and do the comparisons directly with their equipment. Now, the reason we have the generic criteria, the VCA, BC, etc., that I showed on the previous slide, is generally early in the design phase. You know, yeah, we think there's going to be a scanning electron microscope go in this lab, but we don't know what the manufacturer is. We haven't gotten that far. So instead, we can go to the VC criteria, and it says that in general, a scanning electron microscope, if you design for VCD, it should envelope all of the scanning electron microscopes that are out there, right? Same with an MRI. If you design an MRI for VCC, it's meant to envelope all of the different vibration criteria that are out there for MRIs or for scanning electron microscopes. So the VC criteria was actually created a few decades ago with the goal of just enveloping the different types of equipment, and then we can know that, all right, I don't know what my equipment is, but if it's a scanning electron microscope, I can design for this VCC at the end. I can design for VCC and then, or VCD, and then at the, and then I should know that it ought to work for all the equipment that might be possible. So with that, let's look at a little bit more of the equipment-specific criteria. What we've done is we've taken a number of different pieces of equipment that are out there, that are available, and this is for a specific hospital, actually, and then we're looking at how do they compare to each other and against the VC criteria, because it's nice to be able to make an apples-to-apples sort of comparison. And so we took the different criteria, we did a conversion in order to plot it against the VC criteria. And this is what we ended up with here. So we've got various different types of equipment are shown down here. We've got a LINAC, we've got a few MRIs as well, and then they're plotted here, and we see the VC curves. And so we see in general, the worst case is kind of VCD, which is probably, you know, it's reasonable, it's what we're expecting, in the right ballpark. And then we see the other curves are actually less stringent. So that equipment is less stringent than this yellow, the V-Ray LINAC is actually the most sensitive piece of equipment here. Other than at high frequencies, we have something that's more sensitive, but often we're not, the high frequency vibration is not as great a concern as the lower frequency stuff in the 10 to 20 hertz range. So Again, just to repeat, the generic criteria is meant to be conservative. And so as soon as possible, whenever we're aware of what the equipment-specific criteria is, we want to make that comparison, because usually you can remove a bit of conservatism from the design. However, it's not always conservative. Occasionally, you know, there's new pieces of equipment coming out all the time. Occasionally, you'll come across an MRI that you designed for VCC, and then you see, it's actually a little bit more stringent than VCC. So we don't want to be caught being surprised with that as well. So the VC criteria, the generic criteria, is what we designed for in the beginning, and then as early as possible, get that equipment selected and understand what its actual criteria is going to be. So a couple of other concepts when we're talking about criteria is consider the occurrence rate. So if you've got maybe a lab and it's a university setting, and once an hour, a lecture lets out nearby, and you have hundreds of students walking down the hallways, you're likely to have a fairly frequent, occurrence rate. So if you didn't quite hit the criteria for this case, you might be looking at an exceedance every hour, right? For a few minutes every hour. Is that a problem? Versus maybe you didn't design your equipment that you're quite going to meet the criteria under the worst case loading, but you're located somewhere off in a remote part of the building where there's never going to be anyone walking around. And if that's the case, when someone does walk by, it's so infrequent, is it going to affect the measurements? It's going to be so infrequent that you don't really care. You can just redo the measurement. Perhaps these are some things to consider, as how often might your worst case walking scenario occur. Also important to consider the impact of the exceedance, right? If we're in a lab and we have an optical microscope, just looking through it, and if a walker goes down the hall and causes a vibration that exceeds your criteria, and if it's just, you have a blurry image for a second, but then it's restored because the walker has moved past and you can see everything, it doesn't really perhaps affect your the quality of the research being done, because it's just something that's easily recoverable. You can just look at it again and it's no problem. But there's some equipment, if you're looking at something that scans for a long time, maybe takes hours or days to complete a scan, and just the slightest interruption, if you exceed the vibration criteria for just a few seconds, and you won't know that until your scan's done, well, that's a lot of wasted time, right? To scan for 24 hours and then to find out at the end that there must have been something happen because now my image is a little bit blurry in this spot. That's perhaps more important. We need to be a little bit more careful, a little bit more conservative in that design to make sure that that sort of scenario does not happen. So that wraps up briefly what I want to talk about in terms of the receptor and the criteria. We see that there's a number of different criteria that are available. There's equipment specific and there's generic. And so we discussed a little bit about that. Let's move on now and talk about the source. Now, when we're talking about sources of vibration, you could probably name a ton, right? There's those that are external to the building, rail and road traffic. There's construction activity in cities these days. It seems there's always construction going on nearby. And in these cases, we're looking at vibration produced by the equipment, the train or the construction equipment, and it gets in the soil, gets into the foundation of the building, and then can move throughout the building, right? That's external vibrations. And then there's stuff that's internal to the building. There's mechanical equipment, of course, that's operating within the building that hopefully some vibration isolation that's done properly is going to fix that, any concerns around that. And what we're focusing on today is, of course, the last one, which is pedestrians. So people walking around in the building, applying loads, footfall forces to floors tend to create vibrations, and how is that going to affect your lab space? So when we're talking about vibration sources, each one has different characteristics. They've got different frequencies or dynamic frequencies. That's the number of cycles completed in each second. There's different amplitudes of vibration, right? How much the force is or how much the vibration is, the duration, and the number of occurrences, right? These are all things that we consider when we're looking at different sources, and therefore each source has to be handled differently. But we're going to talk about pedestrians, right? Just simply people walking around. And each pedestrian is going to have a walking speed, so measured in steps per second or steps per minute. They have a mass, of course, the more massive, the larger the vibration you would expect, and the number of walkers are of a concern, right? Do you have a classroom getting out when you have hundreds of students walking by, or is it just a single walker? For most lab settings, the case that's considered is a single walker, because it's thought that you're not going to have large groups of people going by, and if they do, it's going to be so infrequent that you don't need to be that concerned. And it's also likely that a single walker will be walking at that worst case walking speed that produces the greatest response. That's more likely than a group of people kind of walking in synchronization. So if we actually look at the walking force that is applied to the floor by an individual, it would look something like this. So this is a plot. Time is on the horizontal axis, and the force applied by the footfall is on the vertical axis. And what we're seeing is large spikes, of course, in this red line, where we have the initial strike down of the heel on the floor, and then the walker moves from their heel, they kind of roll over on their foot, and we see a more complicated waveform, and then you see another large spike. And that's when, of course, if their right foot stepped down, then their left foot, then their right foot, and we're just seeing each of these big peaks, and the response is another foot touching down. Now, what's important about this is that this is a very complicated curve, and we can actually take this signal and we can break it down and look at the various frequencies that are excited. Because when it comes to dynamics, you've probably heard the term resonant frequency before, and that's something that we want to be avoiding as much as possible. And resonance is whenever the natural frequency of a structure, which every floor is going to have a natural frequency, or many frequencies actually, and the frequency of the applied force line up. When they line up, you get a big response, which is obviously a problem. If we take this signal, we break it down. What I want to show here, this is a plot showing kind of the various forces applied at different frequencies. So hang with me here for a second, but what we're seeing is the person's walking at about 2.5 hertz, because we see a big spike here in the force that their foot is outputting at 2.5 hertz. So that means if the resonant frequency of your floor is 2.5 hertz, you're in trouble. But you're probably thinking, well, often floors are a lot stiffer than that, and they are. They're maybe in the range of, say, around 10 hertz or so. There's a lot of floors, 6 to maybe 15 hertz. So you might say I'm clear, but no. In fact, at integer multiples of your walking frequency, you actually get another kind of resonant force that could be applied. So we're seeing another at 5, 7.5, and at about 10 hertz. So if you have a floor with a frequency of 10 hertz, which is not uncommon, you can have that walker is exciting that floor at frequency just because they're walking at a speed that's, in this case, 1/4 of the resonant frequency. So that's great. When we look at walking, what are the speeds we can walk at? Well, most people are going to walk in the range of 1 to maybe 2.2 steps per second or so. And they have an amplitude, I'm saying, they apply a force about 350 newtons. Don't worry about that number, but the walking is often the scenario that we're concerned about the most. Occasionally, we get some more extreme scenarios, and they're very challenging to deal with. And I'm just presenting this for completeness, but if you've got a person running, they run at a much broader frequency range, maybe 1.5 to 4.5 steps per second, right? They're taking more steps in a given amount of time. And the important thing here, so they can excite more frequencies, yes, because they're a broader frequency range. They also have a much larger amplitude. It's maybe 2.5 or 3 times larger, so you can really get a large response. And if you got aerobics or some sort of jumping type activity going on, again, we're looking at a broad frequency range. You can jump up and down at maybe up to 4.5 jumps or steps per second, and the amplitude is around 1100 newtons. So that's about 3 times larger again. So we've got very large forces that can be applied. So all this is to say, walking is challenging enough to design for when we're talking about sensitive equipment in a lab on an elevated floor. If we have to consider running and jumping, it's really, really, really bad. It's very challenging. I would definitely state that you want to keep any sort of fitness room or activity room away from any sensitive equipment that you have. Different floor entirely, a far away floor, and a far away location on the floor plate as well. So with that, we'll move on to the transmission path and talk about some of the analysis and measurements that are conducted to assess vibration. Now, there's several predictive methodologies out there. Over the last 20 years in North America, the most common by far, I would say, would be the American Institute for Steel Construction, or the AISC Design Guide 11. And it came out in 1997, and it was a simplified methodology that worked best whenever it had very rectangular layout floors. So very kind of typical, repeatable bays, very simple structures. And the thing that was curious about it that we disagreed with was that the walking speeds were 50, 75, and the maximum walking speed they considered in the lab, which was 100 steps per minute. And they wouldn't recommend that in the lab. They recommended that in corridors. Those are very, very slow walking speeds. 50, if you get a metronome and you pace out 50 steps per minute, that's less than 1 step every second. And if you had a metronome and you're trying to walk that slowly, you'd probably find it's awkward to walk that slow. 100 steps per minute is getting into a more reasonable sort of walking speed. But again, that's on the low end. Most people, when they're trying to get from point A to point B, just not running or not necessarily in a big hurry, but just going from point A to point B, would walk around 120 steps per minute. So 20% higher than this. And I know from metronomes that I can easily walk on 132 steps per minute. And in fact, I can do 150 steps per minute without too much difficulty. That's if I'm, late for something, I'm walking quickly to get to a meeting or whatnot. I can quite easily do 150 steps per minute for a limited amount of time. Now, there's more advanced predictive methodology that have come out as well. The Steel Construction Institute and the Concrete Center, both out of Europe. And then there was the AISC Design Guide 11, the second edition. So 20 years later, they revised it. And these methods are more advanced. They allow greater flexibility in the analysis that's done. And the second edition of the AISC Design Guide 11 actually updated their walking speeds to be more realistic. So now the maximum walking speed that they're suggesting, I believe, is 126 steps per minute. And so they've revised that up considerably. That's more in line with what we might be expecting. So let's talk a little bit more about the advanced prediction methodologies that are out there. First of all, they employ finite element models. So with computational power, of course, these days, we can build a floor in a finite element program. There's numerous different software packages out there that allow us to assess what the frequencies, what the dynamic properties of the floor are. They can be 3D, so you can look at multiple levels if you have to, and so they're highly advanced. With the finite element model, you can apply the loading to any part of the floor and determine the response at any point on the floor. So previously, some of these simplified methodologies were most effective. Well, they only really worked whenever you're looking at a walker and the response both in the same bay. So if you had someone walking in a corridor that's on the other side of a column line from your scanning electron microscope, it was really challenging to basically figure out what the vibrations ought to be. And they consider many modes. And so I have an image here, animation that's showing the response of kind of a simple floor. So you might think if you jump up and down in the center of a floor plate, you'd see something like this. That's the first mode. But there's a second mode that's shown here, where we've got kind of part of the floor is going up within the structural bay, parts going down. And then there's higher modes. The third mode here is even a more complicated sort of response. Those are all different ways in which the floor can vibrate. A particular structural bay can vibrate in these sorts of manners, but the total response of the floor isn't just the first mode, or the second mode here in the middle, or the third mode on the right. It's a combination of all of them. A person walking across the floor will excite all of these modes, will make all of these modes respond in some fashion. And so we need to know what the total, we need to add them all together and find out what the total response is. And with the advanced finite element models, we're able to do that. We're able to basically look at the floor, get its properties for all these modes, and look at the total response. So you might have a question, all right, that's great if for predictions, if we have a building that doesn't exist, we can do this modeling. What if the building already exists? Is it really necessary to do all these predictions? Well, no, if the building exists, like let's say we have a retrofit and we want a previous space, we want to move a lab in there and putting a scanning electron microscope in there, for instance. What can we do? In that case, we can just go out there and measure it. So measurements determine the conditions that are existing, or we can use it to confirm predicted results. And so with that, show up on site, there's vibration sensors that can measure very, very low levels of vibration, so well below the threshold of human perception. Hook a vibration sensor, an accelerometer, up to the data acquisition system and just measure the response that we're getting and see how it compares against the criteria of the equipment or if it's suitable for the lab. Now, when we're looking at this sort of measurements, there's a few things to consider. We can have a walker. Here I'm showing kind of an architectural plan, and I've got a person walking down a corridor, and they're trying to measure the response that's occurring in a space nearby, right? So when we're doing these sorts of measurements, of course, we have often a single pedestrian because that's the governing source. I mean, if you're concerned about larger groups of people, bring a friend, get a group of people together and do the scenarios that you're concerned with. But a single pedestrian is most common because that's the case we're considering, and we're looking at a constant pace. So this is important because using a metronome, we can make sure we're walking at the frequency that's going to produce the worst case vibration. So if we've got a floor, take some measurements, you should know the natural frequencies of the floor fairly quickly, assess what the worst case walking speed would be, and then just do walking at that speed up and down that corridor just to make sure that you're capturing the worst case response and see how we compare against criteria. Now, of course, you can do realistic walking paths. You know exactly where people can walk. And if you've got doors or something in the way, you should know the impact of that door because you have to physically go through and open that door, and that might cause you to break stride, which slows you down or interrupts the vibration a little bit. And you can be scaled for weight. So you don't have to be just the design weight person is often 170, 180 pounds or so. If you weigh more or less, just scale the final results up or down linearly by that kind of ratio of the person's weight who is walking to the weight of the design person. So we have a case study here I just want to show where, in fact, in this case, this is the most recent opportunity we've had to do modeling. And then a couple of years later, the building was constructed, and we were asked to go back just to verify how things are performing. So it's a steel frame building with bays that are 6.4 meters square, pretty much. The criteria being targeted was VCA and VCB. And whenever we did the predictions, this is the response that was expected. So we have the legend here up at the top of the screen showing workshop through VCA, VCB. So we're looking for the dark blue, and the next shade down of blue would be VCA and VCB. The area highlighted in red here is kind of the area of concern. And then, of course, we have the architectural drawings that are overlaid with this contour map that shows the criteria that's being achieved in various parts of the floor. So over much of the floor, we're in the center of the bay, we're getting about VCA, and then there's a few spots where we're getting operating theater or residential night, and then outside that area where it's not as critical, there's of course higher levels of vibration. So that was what was predicted. We're able to go back and measure in a few spots, and this is kind of what was the outcome. So we've measured in several spots, and we see that in general, yeah, it's matching up with what we're expecting. So that's encouraging. We'll just look at a few of these spots up here on the north end in a little bit more detail, just to see how the comparisons are actually, how they're actually panning out, and look at them in a bit more detail. If we first look at the spot right at the top, we're predicting VCA kind of in the measurements. So it's slow walking within the lab. So if someone was walking basically around this lab space to see what vibrations we can get. And here's an example of what was measured and predicted, plotted against frequency and the RMS velocity here. So we see that both lines, the measured and predicted, are roughly hovering around the VCB line, right? The predicted is actually just over VCB. In this case, at this walking speed, it was just under VCB for the measured. Now there's some more discrepancy at the lower frequencies, This is probably due to background noise. The resonant frequency of the floor is up in this sort of range, around 20 hertz or so, I would think. And then this is probably some sort of background noise that's showing up in the measured response. Now, if we look at another point, it's the point in the adjacent, similar sort of comparison. We're now, in both cases, where the predicted and the measured, we're seeing just over VCB. So it's just hovering around that VCB line, but technically it's VCA. And again, seeing some background noise in the measured results. And then let's look at slow walking within the lab again, but this time near a column. So this measurement was conducted right adjacent to a column. And this is where actually we start to see a little bit more discrepancy. And so what we've got here is the measured, we're getting just under VCC or so. With the predicted, we were predicting about VCE. So what's going on in this case? Well, in this case, it's because we're near a column. We're kind of near the edge of our model, because when we're doing the predictions, we're modeling the floor plate. We have the columns included there, but then you need to assume a boundary condition, right? You need to kind of assume at what point do the columns become fixed, because you're not modeling the entire multi-story structure in most cases. In this case, we're just looking at a single floor. And so this is probably the discrepancy we're seeing here is because of the assumptions made regarding that boundary condition. Nevertheless, the vibrations measured and predicted near the column are the lowest of all, which is what you would expect. I'll point out here too, this one area of the plot where we've got a spike at around 60 hertz or so. So there's a pronounced spike in the measured results. And this is almost certainly a result of mechanical equipment. Something was operating at 3,600 RPM or near there would give us a 60 hertz spike in the response that we're looking at, and that's probably the case here. And so that is important. If it exceeded the criteria, we might have to go back and assess what piece of mechanical equipment was not properly vibration isolated. So just to summarize the findings, the predictions were quite accurate at the center of the bays, right, where you're getting the largest response. Other vibration sources, such as mechanical equipment, must also be controlled. We can't just exclude them entirely. And some discrepancies were near the columns. And in fact, we didn't show this, but when you get further away from the walking path, there's actually, of course, an increase in discrepancies as well. And that makes sense. If you're walking one side of the building, you'd think it'd be easiest to predict the response on that side of the building versus on the other side of the building. The further you get away, the more you're modeling, the greater the transmission path, the more opportunity for discrepancies to creep in. So we'll now move on to the last part of the presentation, where I'm going to talk about some design and mitigation examples. Okay, and when we're dealing with, we'll first start by talking about structural design, and I want to focus on what typical performance you might expect out of various types of structures. So this is very kind of high level, this is very kind of ballpark sorts of numbers, but if you've got a steel structure with maybe a standard 30-foot by 30-foot bay, you might be expecting your steel structure, without any consideration for vibration, to be the workshop to residential day sort of vibration levels, okay? And that's important because those are perceptible, right? That's the human comfort range. Those are quite high levels of vibration. If you're dealing with a concrete structure, because the concrete slab is usually thicker, and often, in fact, the bays are shorter as well, they don't have as long span bays, would probably have a better vibration performance, so lower vibration levels, in the range of maybe residential day through to operating theater. So just kind of above the threshold of human perception. And when you have slab on grade, you're down in the range of imperceptible vibrations here, where VCB all the way down to maybe VCE or so. So this is important because this is saying if we just design for strength and don't consider vibration, both concrete construction and steel construction is likely not going to get us to the range where we need to be for most lab environments. But if we do some mitigation, here's kind of practically where we can get to. And so here's an example of what we've generally found. These are all very rough numbers, of course. Don't take this to the bank or anything. But for steel construction, you can probably get as good as about VCA or VCB in a lab For concrete construction, again, you can normally do a bit better just because of the additional mass and the shorter spans that are usually involved. Maybe VCC or VCD. So that's better, but again, we're kind of up against the limits of what we can do. And I'm saying these are practical limits. We can, of course, always, well, you can often go to larger steel beams. Once you get to the largest steel beam, it's hard to go larger. We can get bigger, but there's diminishing returns. And I think I have a slide here that's showing the sort of mitigation that was required in one example where we had there's basically a grid in the background here. You can see some of them with W18, so this is an American job, of course. Steel sections that are here, and then all these colored lines correspond to changes we had to make to the design to accommodate the vibration performance that was required. So when it was designed for strength, we had to go in and oversize almost everything. We see increased beam sizes and depths, and we also had to change the deck from 3-inch lightweight concrete to 5-inch normal weight concrete because we needed that additional mass and the additional stiffness of that additional material. So things to remember, diminishing returns with additional stiffness. So you might have a floor that vibrates a lot and you can add stiffness to it, increase the sizes of the beams. That will get you so far, right? Initially, that'll get you some pretty decent reductions in the vibration levels. But once you get to very, very stiff floors, like once you've got very large beams underneath your floor, going to the next larger beam doesn't do you too much. In fact, I found that often the increase in the stiffness isn't the thing that's helping you. It's actually you're going to a heavier and heavier and heavier beam, and it's actually the additional mass of the beam is the thing that's helping you out the most because it's harder to lose a larger mass. And so I say here that mass is always beneficial. So going to a thicker concrete slab always helps you out. For example, if you double the mass of your floor, you're going to cut vibrations in half. If everything else remains unchanged, if you double the mass, vibrations are cut in half. So that's kind of the reduction you can be keeping in mind. So often going to a thicker slab is a quick way to get an easy, 50% reduction if you go from a lightweight to a normal weight slab. Increased floor thickness, again, we talked about that with the additional mass and also the additional stiffness that comes into play. And this requires iteration with the architect, the structural engineer, the mechanical engineer, and the electrical engineers. So we're all fighting for the same space. We've got a certain amount of depth that we can work with. If you increase the thickness of the floor slab or increase the depths of the beams, we're cutting into, people start to, lose their space. They don't like that, of course. So it's important, again, to do this earlier in the design so that there can be coordination with the MEP so that we can run the ducts through the floor that we need to. There's been one case I can think of where we had such a large beam, we were supporting an MRI, I think it was 3 feet deep, that they had to actually run the duct through the web of the beam. Right? Yeah, they asked, does that affect things? And we looked into it and it didn't affect things that much, so they put the duct through the beam. So preferably, I think we'd like to avoid that, but occasionally it's what had to be done. So next we'll talk about equipment location. So those are some of the structural modifications. In terms of locating the equipment, this can be, a simple win. So the largest vibrations are at the center of the bay, away from the columns and away from the structural walls. So we have an example here where we've got the red dashed lines and the dots are showing where the columns are and where the column lines are. We've got our walking path, someone walking back and forth just north of this sensitive equipment area that's highlighted. And if we look at the mode shapes or how that floor wants to deflect and move, here's what it would look like. So areas of dark red or dark blue mean that the floor is moving a lot. Areas that are kind of the light yellow mean that the floor is not moving a lot in these areas. So we're seeing along column lines and right at columns, the floor has quite little movement, and near the center of bays, as you'd expect, the floor moves the most. And if we look at the actual predicted levels, vibration levels that we're expecting, it follows a similar sort of pattern. We have the sensitive equipment, we have the walker up here, and then we get the highest vibrations. It's just in the threshold of perceptivity in the center of the bay. But if your equipment is located along the column line here, you're not ISO op anymore. You're now one level lower. So you're getting a better vibration performance just by wisely choosing where you locate your equipment. I'll also state that having a person walk along a column line is beneficial too, because if you want to excite a floor, you jump up and down near the center of the bay. You don't jump up and down next to a column, right? Right next to a column, you jump up and down. You probably won't feel the floor move, but a lot of floors, if you jump up and down in the center of the bay, you've got more leverage on the floor. You can really get it going a lot more. So let's look, just a quick little assessment of the corridor location. Here we have an example. This red line, red arrow rather, is showing where we have a walker. So they're walking hypothetically here within this bay, and here's the response that we're getting in this bay. It's basically workshop. So we have a walker at the center of the bay. We have the maximum response we're seeing. If we now move that walker from the center of the bay, we move him or her off to the side. Again, we see now we have a walker at the edge. We've got a reduction. We're now getting ISO office. So that's a 1 VC class reduction, right? So it's roughly a 50% reduction we might be expecting. Now look at this case, we've got a walker in an adjacent bay. So the person's walking in the adjacent bay, but we're measuring the response in the same bay of concern. Now we're down near residential day. And so that's a reduction of 2 VC classes. So again, this is just showing that having a walker and the receptor in the same bay is obviously your worst case response. The further you can get that walker away from the receptor, the better off you're going to be. Let's talk a little bit about operation controls. So controlled access to corridors. You want to control where your source is, where your pedestrian is. There's certain cases in hospital where you need an access card to get into areas where sensitive equipment is, and they know that the owners know that, yeah, access to this area is going to be restricted whenever there's a procedure being done or where a scan is being taken. So we don't need to worry about having walkers in this area, and that's great. That eliminates the governing source of vibration and helps out a lot. Perhaps something similar can be done in a lab environment. The vibrations might be imperceptible, and it might be not intuitive that pedestrians are causing performance issues. So people might say, why are my images not working out? Meanwhile, they're not realizing that it's the people jumping up and down in the hallway next to them or bouncing around the lab that are causing the issue. So it's important to be aware of how important vibrations are, how they can affect results. Doors can function to control walking speeds. So recall the example I gave earlier. If you have someone walking down a hallway, if that door is not going to be propped open, which is perhaps a big if, then when they get to the door, they need to stop, they push on the door or they pull on the door, and that breaks up the walking path. That slows them down, which can really help to reduce vibrations or reduce the severity of the loading scenario that we have to consider in the analysis. And let other occupants know when vibration sense is in use. So that's a simple thing. If someone's taking a scan, cancel the aerobics class. So these sorts of simple things, if the design team can go for it, if they can agree that, yeah, there's ways that we can control when and where and how people are walking, these are all things that are inexpensive solutions, non-structural solutions that can be beneficial if there's a way to implement them. So just to summarize what we've discussed today, first, I want to emphasize that it's important to identify vibration-sensitive equipment in areas early in the design so that you can properly plan. You don't have to go through and change all of the design that's being conducted on the structure or the architectural layout, whatever the case may be. So identify the problems early. Position vibration-sensitive equipment near columns or along column lines. Avoid having sensitive equipment near hallways or other high traffic areas. Put it off in the basement is preferable, where it's slab on grade, where no one's going to be. Put it kind of down in the dungeon, if possible, is the best spot from a vibration performance perspective. And communicate concerns to occupants. Just be aware of that vibrations can really affect the operation of some equipment. The research is being done, so just be cordial and aware of what the problems might be. So To summarize, the main takeaway is dealing with vibrations is a challenging problem, but it can be overcome. It's important to plan early and to understand what these challenges can be, and simple steps early can have a significant cost savings and improve performance of a laboratory. That brings me to the end of the presentation. Thank you for your time, and if there's any questions, as was mentioned at the beginning, you can type them into the chat window and we can address them.
Thanks very much, Shane. That was quite informative. I'm not sure I'm going to be walking as quite unaware of my steps as I was previously, so I think we'll all be a little more conscious of the vibrations we're generating. I do have one question that's come in. Given that the specific equipment is generally not selected at the time of the building design, how do you take into account the vibration in the early design stages?
Right, that's a great question, and that's one of the challenges, of course, that we're often up against. Is you're right, not knowing what the equipment is means that we have to resort to the generic criteria that I presented at the beginning. So if we don't know what the equipment is, but hopefully we know what type of equipment we're going to be dealing with, that's where we need to move and look at those generic vibration criteria and compare against those. And that's the best we can do. And as I said, they tend to be a bit conservative, right? And there's always uncertainty. So when there are times when we've designed to VCD, for instance, which is quite challenging. And then later on, we get the equipment specific criteria and we see, you know, VCD was effectively overkill for this floor. I mean, it might not have been if we selected a different piece of equipment, but for this particular equipment, it's not as sensitive. So that's why the earlier you can get that info, the better. But with the limitations, yeah, we resort to VC criteria, the generic criteria.
Yeah, which may mean you're essentially over designing.
It can, yes.
Yeah. Okay. Well, I don't see any other questions that have come in, so I guess we can wind things up. And I'd just like to say thanks again on behalf of SLCan for your presentation. It was quite informative. And we appreciate you taking some time out for us today.
Okay, you're very welcome.
Okay, we'll let you go for now then, Shane. Thanks very much again.
Okay, thank you.
Okay.
Take care.
Bye now.